Hi everyone, this is Malika, and in this video, we're going to be reviewing an interesting concept in number theory called the Chinese remainder theorem. So first, I'm going to explain what this theorem is and what it says next, and then we're going to solve a few practice problems that will help us, figure out how to go about solving problems related to this. Let's get started. So the Chinese remainder theorem says that if you're given a system of equations, in this case, you have two, but there could be as many equations as you need. So you have x congruent to A mod P and x congruent to B mod Q. This is equivalent to saying that suppose find a number which leaves a remainder of 3 when divided by 5 and a remainder of 7 when divided by 9. And you're supposed to figure out what that number is. So a question like that. So a system of equations has a unique solution for x mod PQ, which is whatever's on this side, you multiply. So it's modulo PQ. If both P and Q are coprime. So you need to make sure that whatever's on this mod P or mod Q or mod R, they have to be coprime. So what does it mean for two numbers to be coprime? Two numbers are coprime if the greatest number that divides both of them is 1. So the GCD of both of these numbers is 1. For example, 7 and 4. 7 is prime, so there's no other number that divides. And 7 is not a multiple of 4. So these numbers are coprime. 6 and 8 are not coprime because they don't have GCD 1. 2 divides both of them. So the greatest common divisor is not 1. So 6 and 8 are not coprime. Hopefully that makes sense. Okay. Important note before we begin is that if there's more than 2 congruencies, so you have more than 2 equations that you're supposed to solve for, then the moduli must be pairwise coprime so that it doesn't, so if there's 3, then every pair of 2 have to be coprime to each other. And if there's 5, then every pair of 2 within those 5 have to be coprime to each other in order for the Chinese remainder theorem to hold true. So it's just something that we're going to verify each time to make sure that you can get a unique solution with moduli capital N, which would be the product of all the numbers, all the moduli. Okay, so we're going to see that the form of these questions is going to be x congruent to A1, A2, all these numbers here, modulo all these numbers here. And then we know the CRT promises that we, assuming that all the Ni are pairwise coprime, the CRT tells us that there's going to be a unique solution modulo the product of all the Ni's. Okay, we're going to see how to solve questions like this with the practice example. So we know that we're given that x congruent to 2 mod 6 and x is congruent to 3 mod 5. And we need to find the smallest value that for x, which satisfies these conditions. So the CRT would guarantee a unique solution modulo 6 times 5, which is 30. It's the product of these numbers here. Why? Because 6 and 5 are coprime. The greatest number that divides both of them is just 1. So we can use the Chinese remainder theorem here. All right, so now we're going to look at the first congruence. What's another way to write it? So we know that x is congruent to 2 mod 6. So we can write x as 6k plus 2 for some integer, k, okay? And now, since we know that x is 6k plus 2, from this question, we also know that x is congruent to 3 mod 5. So then we know that 6k plus 2 is congruent to 3 mod 5. And now we're going to use mod operations to figure out how to solve something like this. So what you can do is mod operations allow you to subtract. So we're going to get rid of this plus 2 here. So we can write this as 6k congruent to 1 mod 5. All right. And what is 6 mod 5? So you know that 6 mod 5 is 1. So this would simplify to k congruent to 1 mod 5. Okay, so that means now we do the same thing that we did for x here. We wrote x as 6k plus 2. So now we can write k as a function of something else. So we write k would then be 5m plus 1. Okay, And now that we know that x is 6k plus 2, we found that out here. We're going to use k equals 5m plus 1 here. So we write x equals 6 times 5m plus 1 plus 2. And then you get 30m plus 6 plus 2, which is 30m plus 8. And if you notice here, this is the product of all our ni's. So that means we can write this as x. Well, we're going to write this as x congruent to 8 modulo 30. And this is our set of solutions. So the smallest x that solves both these expressions here is 8. And let's verify this. So 8, when divided by 6, gives a remainder of 2. And when divided by 5, gives a remainder of 3, which works. So 8. And then 8 mod 30 will give the set of numbers that satisfy both these equations. Great. Now, let's try solving with 3 congruencies. So this would be a little bit more work than solving with just 2. We're going to do the same thing here. So first, we only consider the first 2 equations. We're going to do it one by one. So x congruent to 2 mod 3 and 3 mod 5. So we're going to take the first one. And since x is congruent to mod 3, we can write it as x equals 3k plus 2. Very similar to how we did the first problem. And now we're going to equate it to the second expression. So 3k plus 2 is congruent to 3 mod 5. It's congruent to 3 mod 5. Okay. And then you subtract the 2. So 3k is congruent to 1 mod 5. So this is basically, you want to find the inverse. You want to find what value when you multiply 3 with what value would you get 1 mod 5. So if you multiply 3 times 2, that gives 1 mod 5. So we're going to do that here. So we write this as 6. So we're going to multiply both sides by 2. So 6k is congruent to 2 mod 5. Right? And now, since we know that 6 is congruent to 1 mod 5, we can just write this as k is congruent to 2 mod 5. Okay? And that means we can write k as 5m plus 2. Great. So now, what we can do is plug this into x. So since we know that x equals 3k plus 2, this is equal to 3 times 5m plus 2 plus 2, which is 15m plus 6 plus 2, which is 15m plus 8. All right, so this is our new value of x that we see here. So x, now we're going to use the third equation. So the third equation is x is congruent to 4 mod 7. So that means, since we know x is 15m plus 8, that means 15m plus 8 is congruent to 4 mod 7. All right, now we are going to subtract 8 from both sides. So you get 15m is congruent to negative 4 mod 7, which is the same as 3 mod 7, right? So now we have 15m congruent to 3 mod 7. And then since we know that 15 can be written as 1 mod 7, this is just m is congruent to 3 mod 7. Because we can just plug in this one here. And then we just left with m. Okay? So m is congruent to 3 mod 7. So that means m can be written as 7. Now we're going to introduce yet a new variable. So let's call it t plus 3. Okay? And now we can just plug this back into our 15m plus 8. So that would be x equals 15 times 7t plus 3 plus 8. So that would be 105t plus 45 plus 8, which is 105t plus 53. So that means x can be written as 53 mod 105. This is our final answer. And the smallest number that satisfies all of these three expressions would be 53. Okay, and that concludes our video. Thank you so much for watching. I hope you learned something new today. I'll see you guys next time. Bye.